Hi there, and welcome to episode 2. In the previous episode, we had a quick introduction to the GPIB bus and the handshaking between the different units on the cable. And today we are taking a look at the actual electronics and the design requirements. And at the end of this episode, we will have a circuit that lives up to these design requirements. So first of all, today I have drawn the input-output buffer circuit required. So what I have drawn here is just one line on the GPIB bus cable. And we have the cable here, and this is the connector. And what we have here is an output buffer that can drive the line. And it basically sends a signal out through here, through the cable, to another device. And up here we have an input buffer. And basically what it is just a Smith trigger circuit to make sure that the signal that comes in here, which might be a bit noisy, is cleaned up here before it goes to our CPU. Also, we need to make sure that the output here can be tri-stated, which means basically the output here becomes high impedant. When this output buffer is tri-stated, the input buffer will work normally. If the output buffer is not tri-stated, that means it's driving the line. We have an output that the signal goes through here. The other thing that is required is that this buffer can go open collector. And basically what this means is that the output driver of this buffer can be in two different modes, which I have drawn down here. The first mode is the normal mode, which is totem pole or pull-push. And basically what happens is that when the input here is high, this transistor will be turned on and the output will be able to sink current through here. So the output will basically go low. On the other hand, if this one is low, this transistor is not conducting, but this one is. So in that case, there will be current running through here. So we are able to either source current or sink current. And this is the normal operation. We can drive the line high or low using this configuration. The other configuration is open collector. In this mode, we have only one transistor. And basically all we can do is that when the input here is high, this transistor will conduct current. So we can pull the signal low through here. However, we don't have this transistor, so we cannot pull the line high again. And what this is used for is when several devices want to get attention from the host. And I have drawn a little example of that on another page here. So what we see here is the input buffer on our host. And then we have 3 open collector circuits, one on each device. And basically what happens is that we have a pull up here. So the signal is normally high on the input to this buffer. However, if either one of those pulls the line low, the input here will be seen as low. So basically this circuit is an OR circuit. We don't really care if whether it's this one or this one or this one. They can both pull the line low. And that is one of the modes in the GPIB bus interface. And finally, we have one more requirement. This circuit must be able to sink 48 milliamps. 48 milliamps. And that is a lot of current. The GPIB bus contains 17 signals. And we need to generate 17 of these circuits. And the question is, how can we do that in a cheap way? Basically, there are 3 ways to do this. The first one, you can buy a chipset that can do that. And we will have a look at that in a few minutes. The other way is that we make this circuit by ourselves. And it's actually possible to buy some logic gates here. For instance, the 74LS244. And this chip can actually drive a 5-meter long ribbon cable. This is not known to most people because it's so commonly used for data bus control in microcontroller circuits. And the third way is simply to ignore all this. Because all these 48 milliamps and the open collectors and stuff like that is for a high-end system that can drive literally tens of different types of equipment. And that is not really what we want to do in this circuit here. When I started this project, I didn't intend to make a full-blown GPIB bus interface that can control more than 2 or 3 devices. Now by snooping around on the internet, I found this chipset from National Semiconductors. And this is fully compatible with the GPIB specification. So if we run through the specifications very quickly, we see that we have 8 lines here on one chip, and on one of the other pages we have the diagram for the other chip. But basically we have buffers in each direction. We have a transmit buffer, and we have one with a hysteresis for the other direction. And we see that the inputs are TTL level, which means that anything below 0.8 volts is taken as a low, and anything above 2 volts is taken as a high. We also see that it has input hysteresis of 400 or 500 millivolts. So that is according to the specification. Now for driving the line, we are able to supply 5.2 milliamps at a voltage of more than 2.5 volts. And also we're able to sync up to 48 milliamps. So of course this chipset is following the specifications as it should. Now with this chipset we can make a 100% compliant bus interface, but of course at a cost. But as I said earlier, we don't really need to be able to control that many devices. And secondly, we don't really need that kind of cost. So that's why I'll take a look at another way of doing it. And well, actually I'm not. Because if we're going to generate 17 signals like that using a 74LS244, we can. But first of all, we need a lot of chips. And secondly, we need a lot of board real estate. And yeah, I don't think it's worth it compared to the National Semiconductors chipset. So this second way of doing it, I've ruled it out. Now, I'm a large fan of microchip PIC controllers. And if we look at the output drive capability of the PIC controller, we see IOH, which is the source capability, and IOL, which is the sync capability. And at 5 volts, of course. And what we see is that we can source around 20 milliamp, and we can sync about 30 or 35. So we are not that far off from the 48 that is required. So for a simple device that doesn't have to control 10 or maybe more devices, this is more than sufficient. So since we need a microcontroller anyway to interface to the USB bus and to accept commands and send replies back to the PC, I think this is quite a clever solution, just to connect the microcontroller directly to the GPIB bus. So basically that's what I have done. So this is the circuit I came up with, and it will be available on my website once I get some time to update it properly. I'm way behind on updating the website, I know. But sooner or later, this circuit will appear there, together with building instructions and everything. But anyway, what I came up with is a PIC 18F24K50, which is a simple small microcontroller that costs less than $2. And it has direct interface to the USB, which is up here. And I connected all the ports here to the GPIB bus interface connector. There is of course a little bit of glue, like a reset circuit, the in-circuit programmer socket, and a couple of LED drivers, which I thought would be nice. So this is my low-cost GPIB bus interface. It's basically a PIC chip at $2, a connector at $3, a couple of transistors and LEDs and what have you, which is maybe another $1, and then the USB connector, which is also a couple of dollars. So for less than $10 component cost, we have a GPIB bus interface. And that's a lot less than what National Instruments are selling theirs for. I also came up with this, which is the full-blown interface. There's a PIC chip with a lot of memory. I think we are talking about 32K words. Then we have a FTDI chip for the USB interface. And we have the 2 National Semiconductors compatible line drivers. And for this circuit, we're talking about $20 to $25 BOM cost. And of course it's a little bit more than the other one. It's more than double actually. But this will for sure be able to drive all the instruments that you need from just this USB bus. You will also notice that the PIC chip that I'm using is not the one with a built-in USB interface. And there are 2 reasons for that. First of all, I hate C and C++, and I love PIC Basic. It just makes the development cycle so much faster. And I don't have a newer version of PIC Basic, so I have to find a chip that was compatible with my compiler. The other reason is that if you're using FTDI chip here, you can use USB version 2.0, which is a lot faster. So this circuit, for sure, I will get going really quickly. And the other solution here that uses a single chip microchip controller with a USB interface, that one I will take a little bit longer to develop the firmware for, because either I have to do it in assembly or I have to do it using C, and I'm not too keen on either. So I guess, yeah, that is the video for today, and thank you for watching, and I'll see you again after I finish the PCB layout.